On November 5, 2025, astronomers at the Lowell Discovery Telescope in Arizona captured an extraordinary image of the interstellar object 3I/Atlas, the third confirmed visitor from beyond our solar system, located at that moment approximately 1.38 astronomical units from the Sun and 2.23 astronomical units from Earth. The image revealed a compact, point-spread function-sized point of light, surrounded by a faint coma-like glow, but lacking any sign of the classic cometary dust tail expected at this proximity to the Sun. Observations were taken through a green filter specifically tuned to the carbon dimer C2 emission band. And while a subtle gaseous halo was visible, its intensity was minimal compared to typical comets at similar heliocentric distances. The surprise deepened when this visual evidence was contrasted with data from NASA's Jet Propulsion Laboratory, which had reported measurable non-gravitational acceleration, an unmistakable indication of outgassing activity, and momentum-based calculations suggesting that if 3I/Atlas behaved like a natural comet, it should have lost more than 13% of its mass by this point in its trajectory. Yet the absence of a visible dust tail implied that either the outgassing was purely gaseous, with little to no entrained particulate matter, or that viewing geometry masked the emission. The November 5th image was taken when 3I/Atlas lay only 13 degrees from the Sun in the sky, producing a nearly head-on viewing angle in which any tail-pointing antisolar would be largely hidden behind the nucleus. This geometry effect could cause even a moderately developed tail to appear as a circular glow, blending with the coma and the stellar background. Nevertheless, this caveat alone cannot fully explain the contradictory nature of the observations, especially given that on July 21, 2025, the Hubble Space Telescope, viewing at a solar elongation of about 10 degrees, had recorded a distinct sunward anti-tail, an optical phenomenon produced when a sheet of dust, viewed edge-on, appears to extend toward the Sun rather than away from it. Hubble's image showed this anti-tail elongated by a factor of 2, demonstrating that dust emission had indeed occurred earlier, though perhaps episodically or directionally confined. The comparison between the two datasets, Hubble's detection of a narrow dust feature in July and Lowell's featureless glow in November, suggests that 3I/Atlas is neither a typical active comet like 2I/Borisov nor an inert asteroid like 1I/Oumuamua, but rather a transitional object exhibiting intermittent or anisotropic activity. Its brightness being greatest in the bluest photometric band also points to an unusual composition or scattering behavior. In most solar system comets, dust grains tend to redden the reflected sunlight, while the dominance of blue emission in 3I/Atlas indicates either extremely fine grains, a gas-dominated coma, or perhaps a highly reflective icy crust that has resisted sublimation. At 1.380, the solar energy flux on the surface was roughly 770 watts per square meter, sufficient to drive intense sublimation in water-ice-rich bodies. So the lack of vigorous dust release raises questions about its surface chemistry and thermal inertia. It may possess a crust sintered by cosmic radiation, creating an insulating layer that suppresses direct sublimation, forcing any volatile release to occur through discrete vents. Such localized jets could easily explain the observed non-gravitational acceleration, as even small asymmetric outflows can impart measurable thrust to a low-mass nucleus. The apparent decoupling between dynamical and optical activity echoes the mystery of Oumuamua, which also accelerated non-gravitationally despite showing no obvious coma or tail, prompting speculation about exotic compositions such as molecular hydrogen ice, nitrogen ice, or even artificial thin film geometry. In the case of 3I/Atlas, however, the detection of weak C2 emissions strongly argues for a natural carbon-bearing volatile source, though the relatively low emission intensity compared with CN bands indicates chemical evolution and depletion of lighter molecules. The surface of an interstellar body traveling for millions of years through the galactic environment would be bombarded by cosmic rays, gradually forming refractory organic polymers that darken and toughen the exterior. When such a body enters a stellar system, solar heat may only penetrate to subsurface pockets of volatiles, leading to subdued activity dominated by gas rather than dust. This could make 3I/Atlas a representative of an intermediate evolutionary state, neither pristine like 2I/Borisov nor desiccated like Oumuamua, but partially devolatilized and crusted, capable of limited gaseous emission without strong dust entrainment. The physics of its non-gravitational acceleration further supports this interpretation. Models of cometary motion show that small but sustained jets can alter an object's trajectory measurably without producing a bright visual display. If 3I/Atlas's outgassing consists mostly of CO or CO2 escaping through narrow fissures, the momentum transfer would still be sufficient to mimic a 13% mass loss signature, while leaving little optical trace. Alternatively, if it ejects comparatively large dust grains, on the order of millimeters rather than microns, these particles would be too heavy to scatter sunlight effectively, rendering the tail optically faint even though mass is being lost. Another possibility is that 3I/Atlas possesses a rotational axis oriented such that active regions periodically face away from the sun, causing transient bursts of sublimation that average out dynamically but leave no persistent morphological feature. Thermal modeling indicates that at the received solar flux, the upper few centimeters of surface material could reach temperatures capable of sublimating carbon monoxide and methane, but not necessarily water ice, consistent with weak gas-only activity. Such conditions favor a coma dominated by small gas molecules, which emit prominently in the blue and green, but produce minimal dust reflection. As the object recedes and its solar elongation increases, ground-based observatories will soon have the chance to observe it under improved geometry. If a dust tail emerges, it would confirm that the November image was deceptive, its tail hidden by projection effects. If, however, 3I/Atlas remains tailless despite cooler conditions and better viewing angles, this would establish it as a genuinely dust-poor body with unusual volatile dynamics. The implications extend far beyond a single object. Every interstellar visitor offers a rare probe into the materials and processes of alien planetary systems. The contrasting behaviors of Oumuamua, Borisov, and Atlas reveal that planetary formation across the galaxy may yield a spectrum of small bodies, some rich in volatiles, others crusted, and still others chemically altered by eons of cosmic exposure. The detection of C2 in 3I/Atlas suggests that organic chemistry is widespread among extrasolar planetesimals, supporting the notion that carbon-based compounds are common in the galaxy and potentially ubiquitous seeds for prebiotic chemistry. Moreover, the object's moderate blue coloration could point to surfaces rich in fresh frost or reflective silicates, hinting at compositional layering produced by differential thermal processing in its parent system. From a dynamical perspective, the persistence of measurable non-gravitational acceleration without visible dust emission provides a critical test for cometary outgassing models. It emphasizes that visible brightness is not always a reliable indicator of activity, and that future missions must integrate spectroscopy and precision astrometry to fully characterize such faint interstellar visitors. The approximately 770 W/m superscript 2 of solar irradiation endured by 3I/Atlas near perihelion likely triggered localized outbursts beneath an otherwise quiescent crust, consistent with the Hubble detection of a narrow anti-tail several months earlier. Those transient emissions may have exhausted accessible near-surface volatiles, leaving the object quiescent by November, its coma faint, but its trajectory still shaped by earlier thrust events. As it moves outward and the solar elongation expands to several tens of degrees, telescopes worldwide, including the Very Large Telescope, Subaru, and upcoming Vera C. Rubin Observatory, are expected to monitor the evolution of its brightness and spectral characteristics. Infrared instruments, particularly the James Webb Space Telescope, could detect residual thermal emission, revealing whether sublimation persists at wavelengths invisible to optical sensors. Whatever the outcome, 3I/Atlas already occupies a unique place in interstellar studies, visibly quiet yet dynamically restless, faintly glowing yet evidencing substantial physical change. Its behavior challenges the simple dichotomy between comets and asteroids and demonstrates that interstellar objects can exhibit hybrid properties shaped by their cosmic histories. Each such discovery enriches the understanding of planetary evolution beyond the Sun, offering a tangible link between distant star systems and our own. The November 2025 Lowell image thus stands not merely as a photograph, but as a puzzle in planetary science, a snapshot of a body that defies expectations, urging astronomers to refine their theories of sublimation, crust formation, and radiation-driven dynamics. Whether future observations reveal a belated dust tail or confirm its enduring minimalism, 3I/Atlas will remain a cornerstone example of how interstellar wanderers can expand the boundaries of known cometary physics. It demonstrates that mass loss, chemical composition, and optical visibility need not correlate directly, and that the faintest of glows can conceal profound physical transformations. Ultimately, this object reminds scientists that the cosmos still holds countless mysteries drifting between the stars, waiting to be illuminated not only by sunlight, but by human curiosity and perseverance in uncovering their stories.